Next, we'll look at a specific series. There's a type of series that's the harmonic series that are like this, but this is the simplest and the one that actually gets the name harmonic series. It's the sum from n equals 1 to infinity of 1 over n. And what that looks like, if I list out some terms, the first term when n equals 1, 1 over 1 is 1. When n equals 2, 1 over 2 is 1 half. When n equals 3, 1/3, 1/4, and so on. It's the reciprocals of the counting numbers added together. And we're not going to look at the partial sums with this one at a time. We're going to use a little bit of a different pattern, which is to use lower bounds that also diverge. So I'm going to do this one kind of informally, but it works if you do it rigorously like this too. Let's list out the first, well, let's see how many we can fit. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And plus, it keeps going endlessly. But this will be enough for us to see a little bit of the pattern. The simple way to do this is to look at these two terms. And we're gonna look at groups of terms. That these two are to get together. 1/3 plus 1/4 is greater than 1/4 plus 1/4. 1/4 is 1/4, but 1/3 is greater than 1/4. Larger denominator here. And this is, so these two together are greater than 1/2. And what I'm going to do is make a series that is smaller piece by piece than this one, than our harmonic series. But, well, I'll keep the first term 1. The 1/2 is, well, it's equal to 1/2, not greater than, but that'll do. If I take the next 4 terms, each of these terms is greater than, well, this one's equal to, but each of these is greater than 1/8. So these 4 terms altogether are greater than 1/8 plus 1/8 plus 1/8 plus 1/8. Which is another 1/2. 4/8, in other words. So if I take the second term, that's a half. The third and fourth terms together are greater than a half. The 5th, 6th, 7th, and 8th terms altogether are greater than a half. The next, I'm going to take 8 terms next, twice as many terms, but I'm never going to run out of terms because the list is infinite to begin with. And so I can always get another 1/2 to add to this. And you can see that this series is going to diverge. It's 1 plus the sum from n equals, it doesn't matter, this is the first 1/2, so 1 to infinity of 1/2. This is an infinite number of 1/2s. So if you add them all together, that's going to be infinity. So I'm not going to say that this equals infinity, but the series diverges because I have a series that's smaller than the harmonic series. This one is smaller term by term anyway, and it diverges, so that the one that's larger by term has to also diverge. This is an important example of the series diverges, the sequence 1 over n equals 1 to infinity. So the underlying sequence, if I'm not doing the summation, but just the sequence, 1, 1/2, 1/3, 1/4, 1/5, those are getting smaller and smaller. The sequence converges. to 0. So the limit as n goes to infinity of 1 over n is 0. And that's it's an important thing to see that even though the sequence does converge to 0, the series itself does not. So that's a divergent series. We're a little more interested in convergent series. You have to be able to identify divergent series, but they're not equal to a number. So convergent series are the ones that are a little more useful. And we're going to look first at a couple properties of convergent series. These don't hold for divergent series, but they're useful for simplifying complicated series. So these are properties of convergent series. We can't necessarily use these properties if it's not a convergent series, but I think they'll make sense. So suppose the sum from n equals 1 to infinity of an equal to, let's call it capital A, and convergent, so it's equal to a number. The series, the sum of all the terms is equal to that number. And also the sum from n equals 1 to infinity of bn are convergent series. And then we're going to have three properties. The first is that the sum from n equals 1 to infinity of the terms formed by adding the corresponding an and bn, so an plus bn. That would be for n equals 1, a1 plus b1, and then plus a2 plus b2 plus a3 plus b3, and so on. That's equal to the sum of the values of those convergent series. Another way to say that is that you can split this sum apart into two sums. The sum of an plus the sum of bn. And then those are the a and b that I named them. There's a second property, and I'll write it down. It's really almost the same as that first property, except we're building a new series using the difference of an and bn. So it's like, it turns out that the series made of an minus bn is the series of an minus the series of bn, or a minus b, as I've called it here. And I've got one more. The sum from n equals 1 to infinity of can is equal to, this is like I'm multiplying all the terms of the an series, multiplying each one by the number c for constant, and the result is c times the sum of the original series. It's almost like we can factor that c out from all of these terms, from infinitely many of them. It's not as obvious as normal factoring because it's not finite. It's a transfinite expression, but it works. Now, the bad news is we can't do anything like this with multiplication or division. If you think about the way that two series would multiply, you'd have to FOIL them, but they don't have two terms each. They have an infinite number of terms each. So you're going to get a new infinite series. It's much more complicated. Nothing as simple as these properties. And then look at example 5.8 on page 455 to see some applications of these basic properties of convergent series. Next, we're going to look at some important convergent series. We looked at the harmonic series, which is an important divergent series, but one of the things that we saw in 5.1 with sequences was the geometric sequence. Now we're going to take a look at the geometric series, which is what you get by adding all the terms of a geometric sequence. And I'll go over that. So for geometric series, I want to start off by looking back at something we saw in 5.1, geometric sequences. So this is just a list. We're not adding them together yet. It's just an, the formula for the nth term, is a number a times a number r to the n minus 1. So the n index corresponds to the exponent on the r for ratio. It's the ratio of sequential terms, ratio of successive terms. Now, for the geometric sequence, the terms are the first one with n equals 1. I'm going to write them as a list. N equals 1 means that's r to the 0, which is 1, and that first term is just a. The next term, when n equals 2, 2 minus 1 is 1, so we've got r to the first, and the factor of a also, so ar. The third term, n equals 3, 3 minus 1 is 2, so we've got ar squared. And you can, no, sorry, not plus yet. Continuing in this pattern, ar to the fourth. The sequence, the terms of the sequence are just, what's happening is the power of r is increasing with each term. So that's what we saw for the sequence. Now the next thing we're going to do with this, the geometric series, is a class of series. If you have an a, we'll assume that a is a positive number. If it's a negative, you just, all the terms are negative. No big difference. The r is what really makes the difference. And let's look at the geometric series, the sum from n equals 1 to infinity of a r to the n minus 1 is, so these are the terms of the sequence are the terms of the series, but now we're actually adding them together to try and see if this is a real number or if it just gets bigger and bigger or doesn't converge at all. So convergent or divergent is the real issue. For this, I'm adding up these terms, and let's look at it like that. A plus AR plus AR squared plus AR cubed plus AR to the fourth plus, and it keeps going in that pattern, just increasing. It looks like a polynomial in R, but it continues. It's not a finite number of terms, so it's not really a polynomial. All right, so I want to look at an example, just a concrete example with a equals 1 and r equals 1/2. That way we're looking at the sum from n equals 1 to infinity of the a is 1 times r to the n minus, I'm not even going to write the 1, I'm just going to write the r, which is 1/2, to the n minus first power, or the n minus 1 power. A is 1, r is 1/2, and that's how I know that this is a geometric series. It's a number raised to the n minus 1, sum from n equals 1 to infinity. If we look at these terms individually, for n equals 1, it's just going to be a if you go by this, but you can also see that if I put in n equals 1, that's 1 minus 1 is 0, 1/2 to the 0 is 1. And then the next term for n equals 2, 2 minus 1 is 1, 1/2 to the first is 1/2. The next term I'm going to have 1/2 to the 3 minus 1, which is 1/2 squared, or 1/4. 1/8, 1/16, and so on. And this is the one that you can see converges by looking at a square of side length 1. Well, there's an extra 1 here. But starting with the 1/2, we can take that square of side length 1, half of it, and then half of the remaining half. And if I shade these, half of the remaining half, half of the remaining half, in the limit, I'll fill up that whole 1 by 1 square. Well, I've got an extra term of 1, so this would actually add up to 2. But it's using the same reasoning as the 1 by 1 square. So I want to erase this example and show you the full story of the geometric series, when it converges, when it doesn't converge, and it's actually a pretty simple criteria, which is if the absolute value of r is less than 1, that is, the ratio or the number r that we've seen throughout all of these, if that number is less than 1, then these terms get smaller and smaller, but also get smaller quickly enough that the series is convergent. So if the radius of convergence is if the radius, the base of this exponential expression is small enough, in other words, between -1 and 1, not including -1 and 1, then the series is convergent. If that r, that ratio, is greater than or equal to 1, then the series is divergent. And this is one of the great things about geometric series. If you recognize a series as geometric, then you can use this simple criteria to tell if it's convergent or not. You kind of have to get it in this form to be able to see the ratio, but then it's a quick decision. Is it a small number or a larger than 1, or larger than or equal to 1 sort of number, including large negative numbers. So that's the geometric series and the results. I want to do a partial proof of this. Not so much this part, you can look in the text, but for this part, there's more. We can get more than convergent. We can actually say what the value of this infinite sum is. And I'm going to show you why, but I need some notes. Otherwise, I'll fuck up. So I'm going to use an expression for the kth partial sum, and I'm going to build it. I'll build the expression before I erase the formula. Defining my series here. This is the expression for the whole series, the infinite sum of all of these terms. What I want right now is an expression for the kth partial sum. That's sk, which would be if I took the sum of all these terms up to and including k, but not beyond k. So the k plus 1 term, k plus 2 terms, all the rest of the terms, I'm truncating to find sk. And I'm going to write down a fairly explicit expression for it. It's a plus AR plus AR squared plus AR cubed plus, and it keeps going all the way up to AR to the K. Is that right? That is not right. What I did there was I just counted up to, well, if I'm looking at the sum of the first K terms, what is that last term? When n equals K, I put not R to the K, R to the K minus 1. And that should be the last term. It's not a huge difference, but technically that is where the partial sum SK stops. So I'm going to use these partial sums to evaluate this infinite series by getting an expression for SK and then looking at the limit as K goes to infinity of the partial sums, and that'll approach this number. Or the limit will be equal to this number. So I need to get some space here. What I'm going to do is assume the absolute value of R is less than 1. And that's the convergent case for this series. And this helps me to do something with this proof. I'm going to multiply both sides by 1 minus R. Now, the reason this is important is if my R was, for example, equal to 1, I'd be multiplying both sides by 0, and that's not informative. But assuming that it's less than 1, first of all, I know it's convergent. This is why, but we're going to see what it's actually equal to when I multiply both sides of this expression by 1 minus R. I get, on the left, 1 minus R times SK. Multiply by 1 minus R. And on the right, uh, 1 minus R times A plus AR plus AR squared plus all the way up to AR to the K minus 1. And multiply both sides of the expression for the partial sum by 1 minus R. Now I'm going to do a couple things on the right-hand side, which is to factor out the A. You see how I have a finite sum here, every term of which has an A. And my 1 minus R, leaving behind, when I factor out that A, it leaves behind the 1 plus R squared, 1 plus R squared, plus all the way up to no A, R to the K minus 1. And now I'm going to distribute this. So I'm working with an indeterminate number of terms in this expression, but it is a finite expression, so normal things like distributing work. And I'm leaving the A factored out. When I multiply through 1 times each of these, let me put this in a box or in a bracket. So 1 times this whole expression is just that whole expression, 1 plus R squared plus all the way up to K, R to the K minus 1. And then minus negative R times this whole expression. Now that's going to be minus. Here I'm taking care of the minus in one swoop. This is all going to be a sum. But R times 1 is R. R times R is R squared. R times R squared is R cubed. All the way up to R to the R times R to the K minus 1 is R to the K. And that's almost readable. Not too bad. What's going to happen here is the same thing that happened in our telescoping series. We're going to have a massive cancellation. And this same computation is done in the text. You want to see it in print. But for this, there's a factor of, or there's a term of r here, and minus a term of r. There's a r squared here, and minus an r squared. And it goes all the way up. Well, there's going to be an r cubed, and there's going to be an r to the k minus 1. It'll cancel with the previous one there. But what doesn't cancel, and what's left from this whole expression simplified, is 1, the first term of this piece, minus r to the k, the last term of that piece. And this is what we're going to use, that 1 minus r times sk, 1 minus r times the kth partial sum, is equal to a times 1 minus r to the k. That's the expression that I'm going to use next, so I'm going to write it up at the top. Uh, 1 minus r sk is equal to a times 1 minus r to the k. So that's why I did this computation, to get that this pretty simple expression is equal to this pretty simple expression. We took some complicated steps, but this is what it comes down to. And we can use this by dividing both sides by 1 minus r to cancel it there. To get the expression for the kth partial sum, a 1 minus r to the k over 1 minus r. And this is a useful expression for the kth partial sum, because we can actually take the limit of this to find the value of the series as a whole. The limit as k goes to infinity of sk, the limit of the sequence of partial sums. So it's a sequence, but each term of the sequence comes from a finite sum. And it's equal to a 1 minus r to the k over 1 minus r. Now I want to remind you that one of the things I required for the convergent case was, well, actually, that's the only requirement. That's it. The r has to be less than 1 in absolute value. It's a small number. And if I look as the limit goes to infinity, as k goes to infinity, that's the only k in the whole expression. I could rewrite this expression as a 1 minus the limit as k goes to infinity of r to the k over 1 minus r, because the rest of this expression, the a and the 1 minus r down here, and even the 1 here, has nothing to do with the k. As k grows larger, well, this is a small number. Small. As we raise it to larger and larger powers, it gets smaller. Like the example we saw earlier, the r was 1/2. Half of a half is even smaller. Half of that is even smaller. Well, as long as it's smaller than 1, this, the limit as k goes to infinity of r to the k, that small number with larger and larger powers is going to go to 0. Raising a small number to a larger and larger power makes smaller and smaller terms. So what's left is a times 1 minus 0, that's a times 1, or just a upstairs, and 1 minus r in the denominator. And that's the formula. I'm going to write that up because that's the final result, but this is the proof of that. The text works it out much like this also. They also show the divergent case, which I really don't care as much about, but for this one, if the absolute value of r is less than 1, so small ratio, then the sum from n equals 1 to infinity of a r to the n minus 1, the geometric series with constant a and ratio r, is equal to a divided by 1 minus r. And this is the formula that is the most important one for geometric sequences or series, because when they do converge, they converge to this, and it's a very simple thing to compute. You just you subtract, and then you divide that number by that, and that's it. So it's a really simple formula. The good news. The bad news is the rest of it is all complicated. So this one, I want to show you with the example that we did before, which I'll write out real quick again. But a was 1, r was 1/2. So we're looking at the series from n equals 1 to infinity of 1 times 1/2 to the n minus 1. And we saw that that was 1 plus 1/2 plus 1/3, no. 1 plus 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th, etc. Now I'm just going to plug into the formula a over 1 minus r, which is 1 over 1/2, which is 2. So I found the value of this geometric series very quickly. It's convergent because the r 1/2 has an absolute value less than 1. That's the one requirement for convergence for geometric series. Now we're going to look at some delicious examples and later on an exciting application of geometric series. Now I wrote up here the formula, which I included the condition. The absolute value of r has to be less than 1 for this to work. But if it is, that implies that the sum from n equals 1 to infinity of the terms of the geometric series each has a multiple or a coefficient of a and the same r raised to the sequential terms, that different n minus 1 values. N equals 1 will start us at 0 for the exponent, then 1, then 2, then, and so on. And the formula is that that's equal to a over 1 minus r. And I'm going to apply that in a fairly straightforward way to this series. Who isn't ready? Totally unprepared here. First of all, notice in my formula that the index in this formula starts at 1. Now, a series can start at 1 or 0 or 5, whatever, but for this formula to work, it has to be the same starting value. And then we have to use the correct numbers for the a and the r, but I can adjust that and make this the series from n equals 1 to infinity by changing the way that number appears in the expression for the terms. So if n starts at 0, the first term here has an exponent of 2, 0 plus 2. So it should be 2/3 to the 2 is my first term. N equals 1 will give me an exponent of 3. So the important thing is that this exponent is starting at 2. We start at 0, the expression n plus 2. We start at 1. I shouldn't have n plus 2 as my exponent. It should be n plus 1. I'm starting my terms, I'm indexing my terms differently. Well, it's kind of the same. I'm just starting from 1. I'm going to have 2/3 to the 2. And that should be my first term. My second term, when n equals 2, will give me the third power, which is the second term of this one. These correspond term by term. So this is the same series written with the notation that we need, which is a series that starts with 1, not the 0th. Next, I'm going to focus on that exponent. Oh, by the way, r equals 2/3, right? That's the base of the exponential expression, the ratio of successive terms. That's 2/3, and the absolute value of 2/3 is less than 1. So this applies, and we can use this formula if we can get this part set up like this. Now, there's another thing that I need to do, which is I want to have my base here, my 2/3, raised to the n minus 1, not n plus 1. The formula I'm trying to use has n minus 1. I need to have n minus 1 in my expression. This is r to the n minus 1, the way I've written it here, but this isn't the same. What I did was I took 2 factors of 2/3 away. I'm going to write it down like this: 2/3 squared. That's 4/9, but if you think of it as 2/3 squared, you can see how I've got the same base here, and I multiply these exponential expressions. I add their exponents, and I get 2 plus n plus 1. Sorry, 2 plus n minus 1. That's n plus 1. The n and the 2 minus 1 is 1. So now I've got this written in a form where I can identify my a and r. For this formula, it's the sum from n equals 1 to infinity of a, which is this number 2/3 squared. 2/3 squared, or 4/9. And r, which is just 2/3, just the base of this exponential expression. And then let me section off those. Those aren't part of my whole thing. This expression that we found is equal to a over 1 minus r. So it's equal to a is 2/3 squared, and 1 minus r is 1 minus 2/3, or 4/9 over 3/3 minus 2/3 is 1/3, and that's 4/9 times 3 over 1, or 4/3. So this series, which we put into the standard form for a geometric series, so it's definitely geometric, by this formula is equal to the number 4/3. So all these infinitely many 2/3 to the different powers, 2/3 to the second is the first one. The first term of this series is n equals 1. That's 2/3 to the 2. Then plus 2/3 to the third, plus 2/3 to the fourth, plus 2/3 to the fifth, and so on. That whole infinite list of numbers sums to 4/3. By the way, this is where we were able to see that it was convergent. So it's worth plugging into the formula. If it's not convergent, the formula doesn't mean anything. I'll leave that formula up, and we'll look at another example that has a different element to it. This one has an R value that is negative. It's not going to make much difference though, because it's a small R value. So this is from, this is example 5.9 from page 458. And part A is the sum from n equals 1 to infinity of negative 3 to the n plus 1 over 4 to the n minus 1. To get this started, I'm going to do roughly the same thing I did in one of the steps in the last problem. This is already starting from 1, so that's good. We don't have to change the indexing or change the expression to start with the first term rather than the 0th. But we do need to put this in the form AR to the n minus 1. That is to the n minus 1, which is good. But this is to the n plus 1. So what I can do is take out from this negative 3 to the n plus 1, take out 2 factors of negative 3, leaving n minus 1 factors of negative 3. So if you think about going the other way, multiplying these together, we would add their exponents. N minus 1 plus 2 is n plus 1. This is the same thing upstairs. Now I've got negative 4 to the n minus 1 downstairs, and this part, this whole piece of the fraction is going to become not this part. Negative 3 squared is just going to, I want to exclude that. I want to look just at this because that's the part where the index variable is. That's the part that's going to give me negative 3. I don't know why I put negative 4 there. Sorry, that's not negative 4. That should just be 4 to the negative, 4 to the n minus 1. It's negative 3 to the n minus 1 over 4 to the n minus 1 is negative 3 over 4 to the n minus 1. That's the quotient rule for exponents. But now we can see it. The A is the number in front. It's the same for every term. Negative 3 squared. I'm just going to call that 9. That's 9. And then the R is this base of the exponential expression, and it is to the n minus 1 power, so this is the right number, negative 3/4. And that is my summary of this geometric series. I know because negative 3/4 is less than 1, well, its absolute value is less than 1. It's a small number, so that's what tells me that the series is convergent. So the convergence of the series is given by this, but since, well, we have it set up like this and we have the A and the R, we can actually find that value. A over 1 minus R, that's 9 over 1 minus negative 3/4. A little bit awkward. That's 4/4 plus 3/4. Which comes out to 36/7, I think. Yeah, that's right. I have another example just to look at the other side a little bit. This is part B for this example. Part B is the sum from n equals 1 to infinity of e to the 2n. to the 2n. Right. And we can write this as the sum of n equals 1 to infinity. Now, I don't want this, this 2n business up here. I want n, well, n minus 1. But it's not a multiple of n by any means. This would be going, the exponent, first exponent would be 2, and then 4, and then 6, and then 8, and so on. It's just going up by 2s. That's not how geometric series works. So what I can do is write this as e squared to the nth power. That's the power rule for exponents. E to the 2, and the whole expression raised to the n is e to the 2n. You multiply those exponents. Now this is almost right. My series starts at 1, n equals 1, but I have an exponent of n here, not n minus 1. This is the, it looks like this is the ratio, but it's not necessarily. The sum from n equals 1 to infinity. If I factor out, well, what can I factor out to get an exponent of n minus 1 there? I would need something plus n minus 1 is n. Well, that's 1. All I really need to do is factor out a single factor of e squared. And then the rest of my bases are e squared. We're pretty much going to stop here. I cannot use this formula because my a, which is e squared, and my r, which is also e squared. In this case, e squared is greater than 1. Actually, I'm going to say it's greater than or equal to, it's greater than. But because of this, I know that this series, it's geometric, but it's not convergent. It's a divergent geometric series. Not very useful because it's equal to infinity, basically. It's not equal to a real number. Now, the application, it's not a life sciences application or a physics application. This is an application of math to math, kind of. We're going to look at a numerical application. And it's a way that we can use geometric series to answer what I think is a pretty reasonable question, but it's not always easy. This is another example. I'm going to leave my formula here because we'll use it. But this is another example, 5.10 from page 459. And there's an error in the textbook. It's just I think it's a plus sign where there should be a minus sign. I'll try not to do that, but the problem here is writing a repeating decimal as a fraction of 2 integers. And this is a simple problem. If you have an irrational number like the square root of 2 or pi, there's no repeating in the decimals. I mean, there's little pieces maybe repeated, but not large patterns. But for rational numbers that are a ratio of 2 integers, the decimal representations either stop or are repeating decimals. A repeating decimal, we'll look at this example, 3.26 repeating. So that's the repeating bar is over the 2 and the 6. So this is 3.26262626, and so on forever. Some repeating decimals have larger periods than this. Some of them are smaller, like 3.3 repeating it's 10 thirds, I think. Anyway, this one though, we're going to look at it 2 decimal places at a time. First of all, it's equal to that 3 in front has really not very much to do with this repeating part. But the 2, 6, right after the decimal place, that's 20, well, that's 2 tenths, but that's 26 hundredths for those first 2. And then hundredths, thousandths, 10 thousandths, that's this part right here is 26 10 thousandths. 100 thousandths, millionths, this is 26 millionths. And there is something geometric about this. Geometric in terms of the way the series looks. We'll get to it precisely in a second, but I'm going to have to put the ellipsis there because I can't fit another one. What's happening is we're increasing the number of zeros in our denominators. That's it. This is 2 zeros and then 4 zeros and 6 zeros, and the next one would have 8 zeros, and so on. I'm going to write that as 3 plus 26 times 1/100th. Not a big difference there, but this will make it easier to look at as a geometric series. Plus 26 times, well, a 10,000th, right? But I can just do that as 100th squared. 100 squared is 10,000. Plus 26 times 1/100th. Well, 100th squared is 10,000, and then times 100. In other words, 100 to the third is 6 zeros. And that gives us the pattern we need to recognize this as not this 3, but all the rest of this is a geometric series. I'm going to write it out here as 3 plus, and I want to keep track of that 3 because that's an important part of the number. It just doesn't have much to do with the series. 3 plus the sum from n equals 1 to infinity of 26 times 1/100th to the, where are we starting here? We're starting at n equals 1, and that's the first term there, n equals 1, and then n equals 2, n equals 3, it's to the nth power. Not exactly what I'm looking for, but almost, and we can get our result from the problem with this is that this is to the nth power and we need the n minus first power. So this is equal to 3 plus the sum from n equals 1 to infinity of 26 times, I'm going to factor out one of those factors of 1/100th and leave the other ones, the other n minus 1 of them. So that the way I'm really going to write my series is 3 plus the sum from n equals 1 to infinity of 26 100ths times 1/100th to the n minus 1. I just stepped on the cat water bowl. And then from this form, you can see what the relevant parameters are in the geometric series, that A is equal to 26 100ths, the R is equal to 1 100th, and we're not trying to show convergence. It's 3.26 repeating. It's a finite number. The way we expressed it as a geometric series, the ratio, or the base of the exponential expression, is less than 1, or absolute value less than 1. It's a small number. So this is convergent. I can use, again, don't forget the 3, but I can use the formula A over 1 minus R. A over 1 minus R. There's A, there's R. A over 1 minus R. To get an expression. The problem asks for a ratio of 2 integers. So I'm going to have to do a little bit of, this is all numerical. I'm going to have to do some arithmetic to get this to look nicer. But it's 26 over 100 all over, that's 100 100ths. Minus 1 100th is 99 100ths. And so the 3 plus 26 100ths times 199ths is going to give me 3 plus 26 99ths. Now that's not a ratio of 2 integers. That's an integer plus a ratio of 2 integers. So I can write my 3 as 99ths. How many is that? 3 times 99, 297 99ths, and plus 26 99ths. That's 323 99ths. Yeah, and so by including this 3 the whole time, I can just summarize my answer in one sentence. 3.26 repeating is equal to 323 over 99. And that's, we didn't really use calculus, but we used the geometric series, which is kind of transfinite. Like, we didn't use infinity at any point, but what we used is the fact that the series is finite, and it makes it convergent to this number. So next we're going to look at some more good news, which is the telescoping series. It's a type of series. We're going to look at it with an example, which is one of the simpler ones. The idea is similar for the rest of them. So the example we'll do is the sum from n equals 1 to infinity of 1 over n plus 1. And we're going to take advantage of the fact that this is a telescoping series. You'll see what that means. First, though, with this particular series, we're going to need to separate this into a sum of 2 simpler fractions using the method of partial fractions like we did with integration. So, partial fractions, we're going to try to write an expression for 1 over n times n plus 1. Already factored, that's nice. But we're going to try and write it in the form a over n plus b over n plus 1. 2 simpler fractions just because the denominators are linear instead of quadratic, simpler denominators. And if we do that, we should be able to recombine those 2 fractions into a single fraction by writing them with the same denominator. Well, this one I'm going to have to multiply by n plus 1. Upstairs and downstairs, I'll get a n plus 1 over, that factor is already there, and this other factor will bring it to, that's what my common denominator is going to be, plus the b only needs to multiply by n over n, so it's bn over n plus 1. Same denominator now. So I I can write that numerator an plus a plus bn all over that common denominator, which means that this 1 has to be equal to this, an plus a plus bn. And it looks like we have one equation with two unknowns, but it's not really. This isn't just a numerical equation. There's three things here, and this has to in fact be true for all values of n. I'm trying to get a formula for 1 over n times n plus 1. It needs to hold in this partial fraction form for all values of n. This is a plus b times n plus a. That a. And what this means is the coefficient of n over here, which is 0. So actually, I'm going to split this into two now. First of all, 0n is equal to a plus b n. So 0 has to be a plus b. And also, 1, the only number over here, is equal to 1, the only, or is equal to a, the only number over there. That's actually one of my coefficients, one of my undetermined coefficients. Well, it's determined now. And then from that, since a is 1, 0 equals 1 plus b means that b is negative 1. Those are my two undetermined coefficients, and I'm going to use them to rewrite my series as the sum from n equals 1 to infinity of, but it should be the a was 1 over n plus the b is negative 1, that's negative 1, over n plus 1. Those are parentheses for emphasis. Those are the partial fractions of this original fraction. They add up to the same thing. Now, what I'm going to do next is use that partial fraction form of the terms to get an expression for the partial sums. And then we'll take the limit of the partial sums as usual and see that it's a real number. But so my kth partial sum, sk, well, the first term is 1 over 1 plus, oh, let's not write it as plus. Each one is negative for the second one, so it's minus 1 over 2. Because n is 1 for the first one. And then the next 1 over 1, 1 over n equals 2. 1 over 2 minus 1 over 3. The next number up. Plus 1 over 3 minus 1 over 4. And you can see where this pattern is going. It's going to end up at 1 over, we're going to the kth term, and that first fraction has that same n denominator. So we're going up to 1 over k minus 1 over k plus 1. And you can see that a lot of these simplify. There's a minus 1/2 and a plus 1/2, a minus 1/3 and a plus 1/3. And that's going to cancel with the next one, and that's going to cancel with, until that's not going to cancel. We're going to have 1 from this first term and 1 over k plus 1 from the last term. That's an expression for the kth partial sum. So if we look at the limit as k goes to infinity of sk, that's the limit as k goes to infinity of 1 minus 1 over k plus 1, which is, you can split this limit further apart. The limit of 1, and then the limit of 1 over k plus 1, or minus that. But what's really happening here is as k goes to infinity, this expression, the denominator goes to infinity, this part goes to 0, and we're left with 1. And that's the value of this series. The limit of the partial sums is equal to the sum of 1 over n times n plus 1, n equals 1 to infinity. That's how we originally encountered the series. The limit of its partial sums is 1, so the series converges to 1.